and thank you for the introduction. Just testing. Yeah, so hi, my name is Steven. I'm the European Regional Manager at Lightbridge. I joined the company quite recently, so please don't grill me during the question area. Slide post is more than enough. So today I'm going to talk about modular type alkaline electrolyzers for mass production. I'm also going to slightly talk about other products that we have to offer, and that might be a good addition for this workshop. So first, let me introduce you to the company. Lightbridge was established in 2012 in Dongtan, South Korea. We are specialized in electrolyzer technologies, and we have over 200 customers in 41 countries, which most are located in Australia, North America, and all over Asia. We're not only designing our own electrolyzer systems, we're also maintaining them and manufacturing them. So we do the whole package. Our year-on-year sales growth is 500%, and on that number you can basically see that the hydrogen demand is really increasing. It's kind of the start of the hydrogen gold rush, I would say. Why green hydrogen, or what's the importance of hydrogen? Basically, first of all, it does not emit polluting gases during combustion and production, so it's a very clean energy, and it's therefore a good substitute for fossil fuels, and subsequently reduces greenhouse gas emissions. It is also a good equality of energy for fossil fuel dependent countries. So take for example Nepal, it's a country in Asia. They don't have their own fossil fuel resources. So they need to import the oil, for example, from China and India. And they want to get away from that dependency. So we have an ongoing project with them. So we gave them a hydrogen fuel charging station and a hydrogen powered vehicle. It's a Hyundai Nexo. You might have seen it on the streets, but there are not so many in Germany here. And they're basically doing tests with the station and the vehicle to find out if the cost savings are sufficient to make the switch to hydrogen. If the tests are good, they will implement it into their public transport network. So they're planning to convert all their buses to hydrogen buses, and then from there go a step further and maybe I'm missing the English word, I'm not native. 1 second. Convert the grid of Kathmandu, the electrical grid, to also be hydrogen powered. Next, green hydrogen plays a big role in creating new jobs. So when the electrolyzer demand increases, there will also be an increase in renewable energy farms. So those need to be built, so therefore creating indirect jobs for that field. A brief summary for alkaline electrolyzers. Most of you are expert in the field, but I just slightly going to touch on it. So it's low cost, long lifetime, and has high nominal outputs of over 100 megawatts, and therefore we think it is the key for large-scale hydrogen production. It is also the longest proven electrolysis process, deployed on a mass scale since the 1920s, and achieves efficiency of 78%, that range. It could be more. We at Lightbridge, we have efficiencies of 82%, and we achieve that by hydrogen plasma coating our electrodes and plasma coating the bipolar plates. And we also design our stacks with the zero gap configuration. Here's a comparison of Alkaline compared to PEM and AEM. I chose PEM and AEM because they are also widely used. So when it comes to cost, capacity, and durability, Alkaline clearly wins that comparison and is therefore very useful or suitable for large industrial use cases. So if you're a big industry or a big company, you want to make a lot of hydrogen, you want a big capacity electrolyzer, which is durable for a relatively fair price. However, when it comes to energy efficiency, it is quite running behind compared to the other two electrolyzer methods, and also the hydrogen purity is lower than the other electrolyzer methods. The purity, however, is not such a big problem because you can just use hydrogen purifiers and achieve the required purity you need. So why do we focus on modular type electrolyzers? So we need to be able to scale fast as the hydrogen demand is increasing fast. So we believe that the best way to scale fast is to have standards, as in having only a handful of available sizes for our electrolyzer stacks. So in fact, we only make 2 sizes of electrolyzer stacks, which I will show later. They're easier to build, and that drives down the production cost, as heavy machinery for the assembly process is not required. Maintenance is also simplified, because when one stack breaks in a system that is made up of multiple stacks, you can just isolate a stack and continue production with a reduction in hydrogen production rate. It is a compact design, so easier to fit and easier to transport. And actually, the transport aspect, we don't build anything bigger than a 40-foot container. So our biggest system would be a 40-foot container, because a 40-foot container is the maximum you can put on a ship in one piece without disassembling it. And the best part is there's no upper capacity limit. So in theory, if required, we could go into the gigawatt range with our electrolyzers, if demand is there. So this is the LBE SC series Alkaline stack. It's our smallest stack size. I actually brought one. I think the online audience can't see it, but it's the size of a big orange. It has an active area per cell of 15.2 square centimeter and a current density of 400 to 500 milliampere per square centimeter at a cell voltage of 1.8 volt. We can only estimate the lifetime, because if you we estimate it to 70,000 hours, but if you really calculate how much 70,000 hours is, it would be like 8 years running it for 24/7. So we're a young company, and these stacks, they're not that old, so we can only estimate it. The operating temperature range is between 15 and 70 degrees. The best temperature, I would say, is 60 degrees to run that. And the power capacity range for these small stacks is 2.5 to 400 watts. So the stacks are customizable. The only dimension that changes is the height of the stack. So depending on how many cells you put in the stack, the higher the stack will be. So you can customize it from 1 to 20 cells, and the more cells you add, the bigger your hydrogen production rate is. And here we got our second stack. So that is the size of a big watermelon. I couldn't bring one. Has an active area per cell of 177 square centimeter, and the current density is the same, 400 to 500 milliampere per square centimeter. We use coated nickel electrodes and porous polymer membranes inside of it, and yeah, we estimate the lifetime to be the same. Yeah, the power capacity range is 150 watts to 8.7 kilowatts. So 8.7 kilowatt would be the biggest stack that we are making. It can be customized from 5 to 48 cells, and that's how it basically looks from inside. Yeah, we're using the zero gap configuration, as I said earlier. The zero gap configuration, yeah, we chose it even though it's a more complex design and it requires the use of porous electrodes. We see enough advantages, which are gives us better cell performance and higher efficiency. It allows for more compact designs, which is very important for modular type electrolyzers, and you can obtain a higher current density with that design. Also, it forces gas bubbles to be released during production that are stuck on the backside of the electrodes. Those are our nickel electrodes. On the right side, you can see one which is not coated. You can see the density is lower than the one on the right left side, which is coated. So by coating it, we increase the conductivity and reduce the resistance. Yeah. So that's one of our electrolyzer systems. It's a 100 kilowatt electrolyzer system, Alkaline. As you can see, it has 10 stacks inside of it. Right there, 10 stacks. So, like I mentioned earlier, if one stack fails, it will just keep producing hydrogen with a reduced hydrogen production rate. The good thing is, as it's modular type, you can just expand the capacity. So if 100 kilowatt isn't enough for your needs, you can go 200 kilowatt by just connecting two systems together. This is the PNID of this 100 kilowatt system that I just showed. On the left hand side, in the middle, you can see all the stacks. And each stack is actually supplied by its own water pump. Those here. So it's not only the stack it's not only when the stack fails that the production continues. No, also the water pumps can fail and production will continue. That's a concept we actually started building in Donghae, South Korea. It's a 1 megawatt electrolyzer, Alkaline at the moment. I'm just going to play a quick video to explain how it looks from inside. Just quick. So on the left side, I'm going to zoom in a second. We have the power supply, it's also modular type. And on the right hand side, we have the PSC. Those two cylinders right here, the thin one is so it's the gas liquid separator. The thin one is the oxygen for the oxygen side, the right one for the hydrogen side. And we also have a water purifier in there. Those are the stacks. Each one can fail and the production continues. And we also have a hydrogen purifier inside of the container, which makes 5.9 purity. On top of the container, we got a heating and a cooling system, so you can basically place the container anywhere in the world at any temperature. And yeah, that's those are other products we have. So this is the last part of my presentation. Here is one hydrogen purifier. It makes a purity of 5.9. It can be connected to any electrolyzer we have. This is the hydrogen fuel station, and we are very proud of it. This is the one I talked about earlier that is deployed in Nepal. The good thing about that fuel station is that there is an electrolyser built inside of it, so it makes its own hydrogen. So you don't have to deliver or supply it with hydrogen bottles. It literally makes its own hydrogen. And if needed, it can also supply electric vehicle with a charging point, but they don't come as standard. Yeah, roughly it makes roughly 20 kilograms of hydrogen per day, but it's also scalable, so it can be more. Yeah, our test stations, we use them to test our stacks. This is how a part of our test report looks like. Yeah, you can play with the parameters and find out the efficiency for your stacks. For example, I'm not an expert in the field for test stations, but yeah, that's how it looks. And then last minute for the company goals 2024, we want to expand our customer base in Europe and South America because we are not very present there. And very important, in order to do that, we need CE certifications and ISO 22734 certifications. So that's a big point. We want to reduce our cost and commencing mass production of our AEM electrolyzers, and we want to finish the megawatt project for our AELN 10 electrolyzers. And the biggest challenge is going to be the construction of our 500 square meter automated mass manufacturing facility in South Korea. We're actually going to have machines that make the stacks automatically, and hopefully it's done by the end of the year, next year. So, alright, so thank you very much for your attention, and yeah, please enjoy your questions.
Thanks a lot for this impressive talk about your technology you have and the equipment you offer. Are there any questions from the audience? Yeah, please, here.
Hi, I'm Yun-Chang from Jungle Production. And if I'm not mistaken, you showed the lifetime estimate, the lifetime of 70,000 hours. That's a very great number. But may I ask how do you get that number?
So we used the test stations basically to see the efficiency drop. I wasn't at the company when it happened at that time, but so they basically saw the efficiency drop and basically calculated how many weeks the efficiency drops by that much, and then they basically thought like, okay, how many years can we go without losing too much efficiency? That's basically it. So, like I said, it's not easy to test lifetime like that, but we're selling those stacks for 3 years, and if in good operating conditions, they haven't failed. And some people run them for 24/7. Yeah. So it's not a guaranteed lifetime. I would like to say that.
So the assumption will be what happened in the first few weeks or months, the degradation mechanism will be the same in the following years.
That's right. So basically, they saw that there was no exponential degradation in the stacks. So yeah, that is an assumption indeed. Yeah. Yeah.
Okay, one question from the online audience. Can you comment on the magnitude of the stray currents, shunt currents in your alkaline electrolysis stacks?
No, sorry. But my email address is below, steven@lightbridge.co.kr, and I can basically refer you to the R&D team, and they are happy to answer the question.
I think it's a difficult question for all of us, but you're experts on that. Any further questions from the audience? Please.
Can you tell us something about the AM stacks? And do you see Lightbridge a future competitor of Lightbridge?
A very good question. So Electrolyser is a great company, and they're way further. They're specialized in AEM stacks, AEM electrolyzers. We are still at the research phase for AEM stacks. So we have one problem, and that's basically the efficiency of our stacks. So right now we are no match for adapter when it comes to AEM stacks. But we are working on it. Like I said, it's in lab scale. We don't do mass production for AM sticks, but we hope that we find a secret sauce to make them right by next year and then become a competitor. Yeah.
Another question?
One question on your last slide, you showed us this refueling station, and on the last row I read electrochemical compression. Are you building electrochemical compressors in the company as well?
So no, the electrochemical compressors are supplied. We're using them, but yeah, they're supplied. Yeah. Yeah.
So there's one further question from the online audience. Do you think that you can expand the current density to 2 amp per square centimeter? Would it be possible to adapt them for that purpose, to increase current density?
To increase the current density to 200 milliampere per square centimeter.
2 amp per square centimeter.
Yeah. And I just don't understand why you would go down with the current density. I think it's better to have a higher current density.
No, higher. It means to go up to 2 amp.
Oh, 2 amp, sorry. Okay, right. No. So we are basically on our limit with 400 to 500 milliampere per square centimeter at the moment. I'm not sure if any research is done to increase the current density, but yeah, it would be great to have 2 amps for sure.
Do you know why it is limited to this current density? Why it's not possible to go to higher?
So the reason is the materials that are used. So the electrode, for example, the coating of the electrode. Yes, actually, now that I think of it, we tried a different coating for the electrodes, and we actually did increase our current density. But when we did that, the production cost of our stacks was just so high that it was not feasible for us to do it. Yeah. So we do it with good materials that are still affordable, basically. And yeah.
Thanks for these answers. So there are no further questions. Then thank again, Stephen, and for this nice talk.
Thank you.
We have now a coffee break, and we will meet again in 30 minutes here.
Kick me now.